Hello. On this adventure in algebra, we will start to study permutation groups. So permutations are going to be defined to be bijections between finite sets. But another definition of permutation we see in lower level courses is just an ordering or listing of distinct objects in some order. And so an interesting application of the theory we're going to study is a type of card trick, or at least a math question. So suppose you take 52 cards in the standard card deck, and you split your card deck into two piles, each of size 26. You do a perfect cut because you're really, really good at working with cards. And then you do what's called a perfect shuffle. And yes, there are people on this planet who can do perfect shuffles. And so the question is, how many times do you need to do this perfect shuffle before you get the same card deck back in its original order? And so what is a perfect shuffle? Well, I'll state it by example. Suppose my card deck has size 6. So if I cut it into two decks, it's A, B, C, D, E, F. Well, then when I shuffle them together, what should happen is that the top card on the left ends up on top, and then they alternate. So it should go A, then D, then B, then E, then C, then F. And so this is, in fact, a well-defined operation. This is what happens when you're shuffling cards the standard way. If the bottom card on this side falls first, then the bottom card on this side, and then they alternate in a perfect pattern. And so there are magic tricks that street magicians use that rely on their ability to do a perfect shuffle. And so at least one of the tricks would involve actually knowing how many perfect shuffles you need to do in order to get the deck back where it was. So for instance, if they had the audience member draw out a card and they knew exactly where the card got put in the deck, they do the perfect shuffle a certain number of times and then they reveal what the card was. Alright, so now we're going to actually do some group theory. Given any finite set, any set X, we're going to let S sub X be the set of all functions sigma from X to X. So the domain of the function is X, and the codomain is also X. And our requirement is that sigma is a bijection, so it is one-to-one and onto, or it's injective and surjective. So it's worth noting, this set is a set of functions. So for instance, if we let X be the set 1, 2, 3, we're looking at functions from 1, 2, 3 to itself, with the property that you end up with a bijection. So let's decide if we're going to send 1 to 1. Well, in order to be injective, we can't send anything else to 1. So 2 has to either go to 3 or 2. So let's decide to send it to 3. Similarly, whatever I do to 3, I can't send it to 1, and I can't send it to 3 because then my function won't be injective, and so I must send it to 2. So this is an example of a function that is a bijection because it's injective, and you can see that it's also surjective because for every y value, there is an x value such that sigma of x is equal to y. So this particular map is in S123. Which is often abbreviated as S sub 3. So whenever the set you're working with is the integers 1 through n, we'll often use S sub n instead for shorthand notation. So the elements in this set are functions, and in fact they're bijections. The claim is that this set is actually a group under composition. So of course, what do we mean by composition? we mean for any x in your set X, you define the composition of two functions by first applying tau to x and then applying sigma to it. Because the domains and codomains are all the same, this actually is a well-defined function with domain and codomain x. And most importantly, this group has a special name. It is called the symmetric group. So we're going to claim that we have a group. In this case, it's worth pointing out that it's not obvious that this operation is well-defined, in the sense that it's not clear that if you compose two functions that are bijections, that the result is going to be a bijection. So this is one of those cases where we do need to check closure. So in other words, this is just pointing out, given two bijections, sigma and tau, then their composition is also a bijection. I'm not going to prove that in this video. So a lot of the proof of this theorem are going to be held off for the next part, because these are facts from Math 3350. So if you remember these facts from Math 3350, you can skip the next video. If you don't, I'd recommend watching the next video. In order to be a group, you need the associative axiom. So for any three elements in your set, you need to know that the product is of the three elements is the same no matter where you put the parentheses. Again, we're going to check that in part 2. Notice I'm stating it for functions instead of bijections, because actually this is a claim in Math 3350 as well. And so this is actually true for any three functions as long as the domains and codomains all work out correctly. So in particular, it's also true for bijections. And so associativity holds. Of course, what else do we need? Well, you need an identity. The identity element is going to have to be a bijection, such that when you compose it with any other bijection, you get the other bijection back. It turns out the correct definition is this function. You define it. It's a function from x to x. And for every point little x in your big set, you define it identity of the little x to be little x. So you need to check that this is in fact a bijection. It's not too hard to see that it's injective, given two elements little x and little y. If ID of x is equal to ID of y, well, by definition, ID of x is x, ID of y is y, and so behold, x is equal to y. So if f of x is equal to f of y, then x is equal to y. That's the definition of injective. Surjective, what do you need to check? You need to check for every y and x in the codomain. There exists an x in the domain such that f of x equals y. Well, in this case, x equals y does the trick. So it is surjective. So it's trivially a bijection. More importantly, if you let sigma be any other bijection and you let x be any other element of x, then the identity function composed with sigma by definition is composition is this, identity of sigma x. Identity of anything is just that anything. Similarly, if I do sigma composed with the identity of x, that's sigma applied to the identity of x. By identity of x is just x. And so what we see, since x was chosen to be an arbitrary element of x, we get that identity function composed with sigma is equal to sigma. Now, this is the definition of equality of functions, if you might remember. To say that two functions were equal, they had to have the same codomain, the same domain, and for all x in the domain, f of x had to be equal to g of x. So that's what we just checked. Similarly, this equation told us that these two functions have the same y values for every x value, so they're the same function. And so congratulations, if you compose on any bijection on the left or right by the identity function, you get that bijection back. Therefore, the identity is a multiplicative identity. So we've got the associativity, we've got our identity function. The last thing we need is the existence of inverses. And so a theorem that was on the first worksheet is that a function from a to b is a bijection if and only if it has an inverse. That is, there exists a function g from b to a, such that f composed with g is the identity function from b to b, and g composed with f is the identity function from a to a. Note here, the advantage of this identity function is I'm able to state this fact more succinctly. Sometimes we actually write these two properties with a universal quantifier. So this is a theorem that I'll reprove in the next video in case you've forgotten it. But we know it's true. So let sigma be any bijection. Then by this theorem, there exists a tau that satisfies these two properties. So it looks like tau plays the role of sigma inverse. In order to state that for sure, we have to point out that tau is a bijection as well, so that we know that tau is actually in this set. Because right now it's just a function from x to x. But you apply this theorem again to tau, and applying this theorem to tau tells us that since tau has an inverse with respect to composition, tau is a bijection. So the first direction, because sigma is a bijection, it has an inverse. This reverse direction, because tau has an inverse, it's a bijection. So tau is in the symmetric group. So sigma inverse exists. It's this tau. And in case you skip the next video, this inverse permutation is given by the following condition. Sigma x is equal to y if and only if sigma inverse of y is equal to x, where x and y are any 2 points in x. So you have one condition if and only if you have the other.